that introduction. So I noticed in the program that it says 13 minutes plus 5 minutes for questions. And I think the idea was that I was supposed to talk to you for about 30 minutes, and then you would ask me questions for 5 minutes. Oh, we've gone blank. There we go. Actually, I'm going to spin that around a little bit, and I'm going to start by asking you some questions. Okay? So, just like you to raise your hands. Who out there has knowingly used some form of encryption in their time? Okay, probably this audience skews it a little bit. That's fine. That's fine, no problem there. I'll raise my hand as well. I've used encryption, I've used WhatsApp, that kind of thing as well. Okay, who's signed their name at some point in their life? Yeah, no surprise, the whole audience. Okay, that's fine. I think, yeah, this audience skews it very slightly, but generally I find that it's about half the audience say they've used encryption, everybody says they've signed their name. And the point is, of course, signing your name is something you do much more often than using encryption. So signatures are something that are perhaps a bit more useful than encryption. But do you ever think why you actually sign your name? Does anyone have any ideas? Why do you sign your name? What's the purpose behind putting that ink mark on a piece of paper? Thank you, Iris. Ross, you didn't need to step in this time. Co-author there was trying to step in. Authentication. I'm glad you put it that way as well. Authentication. That's one of the key reasons for using signatures is authentication. So if I put my name on a check, for example, you will know that that check came from me. Now, built into that is something called transferability. So if I give you my check, you then take it to the bank sometime later, you're trusting that the bank will also verify that signature and say that it's from me. So that's transferability. And then there's non-repudiation. So if it's, for example, a contract, I can't say, oh no, I go back on what that contract says. I've put my name on it, I stand by what it says. Now, I admit, if there's anybody from an information theory background here, I'm being a little loose with my definitions, but for the purposes of this talk, I think they'll fit what we need to do. And with this simple system of just sort of pen and ink mark, we created a system that allows us to change the world. We can put our name to something and to change the world. But the thing is, we don't live, well, theoretically, we don't live in a paper world anymore. We're supposed to live in the paperless office, the digital world. We all carry around with us these powerful computers with built-in cameras. And now suddenly we have this way of transmitting messages electronically. But also, your little signature there, your pen and ink signature, suddenly just becomes a graphic, a series of ones and zeros that can be stored digitally and reproduced many, many times, each copy being absolutely perfect. So suddenly, this signature of yours can be appended to any message that somebody chooses, and you have no control over it. So what we need is some way of creating a signature for a digital message, a digital signature. Now thankfully these things do in fact exist, and they've been studied now for something like about 30 odd years, and they're typically based on what are called trapdoor one-way functions. Now, trapdoor one-way functions, if I get into the technicalities of them, can be very complicated to explain. So let me just try and explain in a very simple sense. They're a mathematical function that is very easy to do one way, not so easy to invert unless I give you some prior information. That's the trapdoor, the information that allows you to invert the function. So think of it a bit like baking a cake. Very easy to take the ingredients, that's my sort of secret information, and my message, process it through some kind of function, that's baking the cake, and then produce the cake at the end. That's my signed message. Not so easy, but not entirely impossible, to take the cake, process it through some kind of function, and go back to the original ingredients. Now I say not entirely impossible because, in principle, you could sit there and you could pick this cake apart at an atomic level and go back and put it back to the original ingredients. So these things have been around for a while. Buried very deep in your options for Microsoft Outlook is the ability to sign a digital message. So deep you'd think Microsoft probably didn't want you to actually use it. I'll not comment on that further. Additionally, anytime you see the padlock icon appearing in a web browser, that's digital signatures in use. And certainly in the UK at least, if you're using chip and PIN to pay for transactions, that's digital signatures in use as well. So this scheme, widely adopted, widely in use, but there is a potential problem with it. All of the security is based on that perceived complexity of inverting the one-way mathematical functions. And that is just computational complexity. It's what we call computational security. It's only guaranteed so long as it's difficult to actually carry out the inversion of that mathematical function. And this is something people have been looking at. The much vaunted quantum computers, most of the algorithms we know for that are also algorithms that will be able to break a lot of the digital signature schemes that are in use at the moment. We may come up with new algorithms which will allow us to break digital signature schemes much more easily. And we can even try simple brute force attacks to try this, where we simply try every single possible combination. And these are all ways that we can break these digital signature schemes. Now you may say, okay, I'll just extend the length of my signature bits every time that Moore's law, and I know this isn't exactly Moore's law, but it's proportional to it. Every time Moore's law says that our computational speed increases, I'll just extend the length of my signature bits. But the problem is that all of those messages you stored previously can now be broken progressively more and more easily. Now that's not a big issue if you're dealing with something like your credit card that's probably expired. But if it's something such as your health records or other government data, that's actually quite a big problem. And of course, that still doesn't get us around the quantum computer and the improved algorithms. There is a field that looks at this, and it's typically called post-quantum cryptography. Now the name post-quantum cryptography is a little misleading, because post-quantum cryptography also includes quantum key distribution and quantum digital signatures. But it also looks at mathematical approaches as well. So I'll focus on quantum digital signatures in the rest of this talk. Quantum digital signatures excuse me, were first proposed in 2001 by Guzman and Chung in a paper that still remains on the archive. Now the problem with that protocol was that it required a experimentally very difficult to implement swap test. That requirement was removed in 2006 by Erica Anderson and her colleagues, and we carried out the first experimental demonstration of that protocol in 2012. Now the problem with the way that we implemented that was, although we'd removed the requirement for the swap test, we still had some requirements that made this still very challenging, that limited our length of operation and the stability of the system. We also required some form of quantum memory in this implementation. In 2014, we were able to remove that requirement for a quantum memory. In 2016, we were then able to extend to kilometre ranges in the laboratory. Later that year, we were able to go to installed fibre, and then we were able to extend the distance of installed fibre early this year. And those last three papers are the ones I'll mainly cover in this presentation. And the last 4 papers or so were carried out as part of the Quantum Communications Hub, as part of the UK's Quantum Hub project. So you may not be entirely familiar with quantum digital signatures. Let me just give you a quick introduction to how they work. We've got our sender and our receiver, Alice and Bob, same as it is in QKD. Alice now has her signature that she wants to transmit to Bob. So what she does is she encodes this on a series of phase-encoded coherent states. So already we have a difference from QDS to QKD. Here we have phase-encoded coherent states, and it's a sequence of them. They're chosen from the set 2 pi k over n. N is your number of phase encodings, and your number of phase encodings is one parameter in your security analysis for this. So you don't necessarily just have the typical 4 of QKD, you can have many of them. And depending on the amplitude of your coherent state, of course, as we all know, for higher amplitude coherent states, it can be very easy to tell these phases apart, but as you reduce the amplitude, it becomes harder and harder to tell them apart. So the amplitude of the coherent state becomes another parameter in the security analysis of this. Now, unfortunately, I don't have time to go through the full security analysis of QDS. I can give you sort of a basic grounding in it, but the original paper on QDS, experimental QDS, was about 3 or 4 pages of journal format to explain the experiment, and another 30 to 40 pages to explain the theory. So I can only touch on it briefly here. As I said, it's a series of coherent states that are sent from Alice to Bob. and there are many used to sign a single bit. Unlike QKD, where we have a processed pulse, one single processed pulse is used to secure one bit. Here we have many processed coherent states are used to sign a bit. And you use two different sequences, one for a 0 and one for a 1. Nobody except for the sender knows exactly what the coherent states you've used are. So only the sender can provide a full classical description of exactly what phase is used in each coherent state. And that's how you get the authentication. If somebody can provide an exact list of every single coherent state that was used, you know that that person must have been the original source of the sequence. And this is information theoretically secure to within certain boundaries. Now the problem is that message transmission might take place a long time after the quantum states have been sent. Now that's not a problem in classical systems, because of course you just store the classical data, but for this original approach you need to store the coherent states in some form of quantum memory. So let's look at a specific example using 4 states, the same 4 states as in BB84 QKD, 0, pi by 2, pi, 3 pi by 2. Alice sends, and we've got Alice, Bob, and Charlie here because we want to now look at transferability. So Alice sends her coherent states to Bob and to Charlie. They make measurements, sometimes making a failure, and that means that they end up with a partially correlated states between Alice and Bob and Alice and Charlie. They then also forward some of these states to each other, and that means that we now end up with partial correlations between Bob and Charlie. So we now have a triangle of partial correlations, Alice to Bob, Alice to Charlie, and Bob to Charlie. And that's what gives us the security in QDS. Nobody has the full information on the sequence apart from Alice. And then, of course, as I said, Alice signs the sequence by sending a classical list of the descriptors of the state. Now there's one more parameter I need to introduce, which is the security level epsilon. And to compute the security level epsilon, we calculate the probability of a signature being successfully forged, the probability of an honest signature being rejected, and the probability of repudiation of a valid message. In a typical system, we have no reason to preferentially pick any one of these probabilities to be higher than the other, so we set them approximately equal and then say the system is epsilon secure if all of these values are less than or equal to epsilon. And you can think of epsilon as being the probability of this system failing in some respects. And all of these parameters depend on the length of the sequence that you use, the number of photons in per pulse, the number of phases in your alphabet, the error rate, and your transmission distance. So they're all very system-specific, long calculations. So we carried out the first experimental demonstration in 2012, and I'll show it here just for historical reasons. On the left-hand side here, we have a quantum key distribution sender, Alice. We've got our phase modulator there to set the state, and an air gap to provide a delayed phase reference, because phase is a relative measurement. And then the receiver, we just have the same process in reverse to allow us to read back the states. The difference is in the middle we have this thing called the multiport. And it might be quite difficult for you to realize what the multiport is, but if you sort of tilt your head to the left or to the right 45 degrees, I hope you can see that it's 2 interwoven Mach Zehnder interferometers, just textbook Mach Zehnder interferometers. And that's how we do the transfer of the information from Bob to Charlie. If we take a look at the signature coming into, I'll tell you what, I'll pop up here. If we take a look at the signature coming in from here, Bob's copy comes in, is split half by amplitude and sent half to Charlie, and then Charlie's done exactly the same, split off half by amplitude. So they both combine half by amplitude here on this final beam splitter, and if the signatures are exactly the same, they should receive the original signature out through this port, and if there's any differences, they'll get light coming out through this port. So we put simple binary Geiger mode detectors on here, and if we detect anything here, we know that there was a problem with the signatures being sent to Bob and to Charlie, and they can stop and abort the system. Now the problem with this is that, as I said, we can sometimes have a delay between the coherent states being sent and the message being sent, which requires us to have some form of quantum memory. Here we just used short delays between the multiport and the receiver systems, and that just allowed us to have a long enough delay that we could send the signal from the phase modulator in Alice to the phase modulators in Bob and Charlie. But of course in a real system, that's actually quite a problem. However, you can actually replicate almost all of the functionality of the multiport classically by looking at the results from your detectors. So if we look at how that system can be set up, you can see that we very quickly got rid of the multi-port. Now, and that's allowed us to put in several kilometers of fibre, and that's because the multi-port there had a loss of about 8 dB. Additionally, because it was an interferometer, it limited the size of operation of this system. So here, the difference between Bob and Charlie was only about 5 meters, whereas now, if we remove it, we have the ability to insert several kilometers of optical fibre. This approach used unambiguous state elimination in the detector scheme, which is why there are 2 sets of interferometers there. And unambiguous state elimination might be unfamiliar to you, so I'll just quickly summarize it here. We have the 2 interferometers, and we set one up with a fixed phase delay, which allows us to tell between states with the 0 and pi phase round. And we set up another one which has a delay which allows us to tell between pi by 2 and 3 pi by 2. So if we look at a 0 incident phase, obviously each detector cannot tell us exactly what a phase is. It can only indicate what a phase is not. So if we had an incident phase of 0, we'd expect detector A to fire, detector C to fire, and detector D to possibly fire. Now, if we had all 3 detectors firing and detector B not firing, that would be unambiguous state discrimination, and we would know exactly what the phase was. But in reality, we're working with weak coherent states, so they have a low mean photon number, and we're working with non-unity detectors, and we have loss in our system. So it's very unlikely we will ever actually get those 3 detectors to fire and the one not to fire. But even one detector firing still gives us partial information about the actual phase of the state, and that's information that we can bound relative to that known to an eavesdropper, and we can still factor it into the security proof. So this implementation allowed us to go up to kilometer ranges, and it was tested at ranges of 0.5 kilometer, 1 kilometer, and 2 kilometers over a number of different mean photon numbers per pulse. And you can see that at the low mean photon number per pulse, we've got quite a long time to actually transmit the signature, so up to somewhere about just under 1,000 seconds there. And remember, as I said, these figures might look a bit bad compared to quantum key distribution, but we're talking about many pulses to sign a single bit. So at those lower mean photon numbers, that was mainly due to detector noise. We simply didn't have enough counts arriving at our detectors, and the measurements were dominated by detector noise. Then at the higher mean photon numbers, we simply had too much energy arriving at our detectors, and we were starting to see non-linearity effects. But still, we were able to get an approximate optimum value around 0.4 photons per pulse at both 0.5 kilometer, 1 kilometer, and 2 kilometers. This protocol leads into a slightly revised protocol, which allowed us to then go over far longer distances. So we go back to our triangle of Alice, Bob, and Charlie. But here now, Bob and Charlie become senders who carry out partial quantum key distribution with Alice. So they carry out quantum key distribution up to the point of generating a sifted key. So they don't go through error correction and privacy amplification. They just get to the point of basis set reconciliation. This means they essentially transmit 2 random sequences, one for the 0 and one for the 1, to Alice. So they end up with 2 partially correlated sequences. They can then carry out full quantum key distribution between each other and forward half of the bit sequences to each other, meaning they now end up with partial correlations between themselves there. And you can see that we're now back to the triangle of partial correlations we had at the start of the earlier protocol, which allows us now to do quantum digital signatures with this. But instead of using a custom protocol, we're just using quantum key distribution all the way through this process. So suddenly it becomes possible to do this with quantum key distribution hardware and not customized hardware. Now the security analysis of this relies on the security of the underlying quantum key distribution protocol and builds upon it. And this has been widely studied for the BB84 in phase quantum key distribution protocol. However, when we went to experimentally demonstrate this, we partnered with NICT in Tokyo, and we only had access to a differential phase shift QKD system. This is great because there's no basis set reconciliation required. Essentially what you get at your detectors is what you use. However, there's only been a limited security analysis carried out compared with other quantum key distribution protocols. And we saw a little bit of DPS in Jake's presentation before, but I'll just quickly summarize how DPS is different here. We've got our CW laser and pulse carving with an intensity modulator to make it pulsed. Then there's a phase modulator that in Alice, or Bob Charlie here, that selects between 0 and pi. Attenuator to take us down to the required mean photon number per pulse. Transmit through the optical fibre. Then at the receiver we have a 1 pulse period delay, so that each pulse is interfered with the successive next pulse. So therefore, if the pulse difference between two successive pulses is 0, SNSPD2 will fire and will register a bit value of 0. If it's pi or minus pi, the other SNSPD will fire and will get a bit value of 1. So it's a very simple process to implement and therefore very attractive to implement. But the security proofs have not been so widely studied. We built on the best security proofs that we could find for DPS QKD to allow us to actually carry out an analysis of the security approach here for QDS. And these protocols, these security proofs, they do have the limitation that they don't look at composability of attacks. They only seek individual attacks. So it means that our values may not be exactly the best signature timings possible, but they are indicative of those that are possible with this system. So we used a link in the Tokyo QKD network for this, and it was a link between Kogane and Otomachi. It was approximately 45 kilometers long with a total loss of 31 dB. 50% of it was underground and 50% of it was in an aerial connection. This was dark fibre, so there was no other transmission other than the quantum transmission. However, it was installed fibre. So as I said, 50% of it was nice, well-protected underground optical fibre like this, and 50% of it was hanging in the air above the streets like that, which is why the loss is higher than you potentially expect for those sorts of lengths of optical fibre. So just to show the previous results, this is our 1 megahertz unambiguous state elimination experiment at 0.2 photons per pulse, and this is at 0.4 photons per pulse, the optimum value. You can see that we're talking about a few hundred seconds there to transmit the key. These are the results from the Tokyo QKD network. The 90 kilometer result is the actual link, and an additional attenuation was introduced from ND filters to allow us to simulate longer lengths. And you can see that we're much faster in the transmission there. So we've gone, in the space of approximately 5 years, we've gone from being able to work over 5 meters in a laboratory environment to being able to work over about 130 kilometers in installed optical fibre. And we've gone from being of the order of a few hundred seconds to transmit a key up to the order of a few tens of seconds to transmit it. Now I know the title of this presentation was Optical Fibres. However, I'll just show this point here, which is a free space link carried out by some of my colleagues in collaboration with St Andrews, Max Planck and Erlangen, and that was over 1.6 kilometers. Now that's using a CV QKD system, so you can see that already we're starting to look at other QKD systems that can be applied to that. Now all of these experiments shown here were carried out at an epsilon 10 to the minus 4, and that's generally been used up until now as the value for quantum digital signatures. However, quantum key distribution experiments tend to use values around 10 to the minus 10. So to compare the results of the systems, our two systems, at 10 to the minus 10, you can see in the left-hand column there's a laboratory-based system taking approximately 40 seconds to 1,600 seconds, depending on the length of optical fibre in use. And then the latest work in the installed optical fibre being approximately half a second to 20 seconds, depending on the length of optical fibre in use. So because these can be applied to almost any quantum key distribution experiment, some of my colleagues have been working with groups in China on the HiFi optical fibre network, and they've been working with measurement device independent quantum key distribution to use it for QDS. Now, MDI QKD works a little bit differently from all the QKD protocols you've seen before. Now, you have a party in the middle, who here confusingly is labeled E, who serves as the actual measurement device. And this means that you don't have to trust your detectors. It gives you a higher level of security. I'm being a little lax with my terminology here, but it gives you a higher level of security than you would with other approaches. So they set up a system with various different branches of optical fibre, and again installed optical fibre in an urban environment. And you can see that A to E to B was the protocol up until the point of assisted key generation, as was A to E to C, and then B to E to C was the full QKD allowing for the swap test between that. Now, I stress that this protocol is far more secure because of the use of MDI QKD. However, MDI QKD is a very immature technology. People are still researching this, and some of the clock rates and some of the bit rates are not as high as they could potentially be in other applications. This means that they only used a 75 megahertz clock for this, and it would take them approximately 41 hours to sign a single bit at an epsilon of approximately 8 times 10 to the minus 10 there. So although you get the improved security, unfortunately it does take a little longer with this approach, but there is the scope that MDI QKD could be considerably improved in future. So, to summarise, we've successfully carried out the first demonstration of quantum digital signatures in installed optical fibre, and we've proven that quantum key distribution hardware can be used for QDS with only minimal modifications. So what's next? Well, the first thing would be to develop a reconfigurable QDS testbed for use in dark fibre. Then we'd like to apply the lessons learned to experiments in the UK quantum network. Now, you may not have heard of the UK quantum network, so there's a diagram of it shown there. And as you can see, it covers the important parts of the UK, meaning that Heriot Watt is somewhere up on the ceiling somewhere. So there's a link there in Bristol, and I believe that's already installed fibre that's accessible to Bristol University. There's a connection onto Telehouse with BT are in London. There's a connection down to Southampton University. There's a connection up to a local area network in Cambridge, and there's a connection out to Martlesham where BT have their labs at Adastral Park. And the hope is to be able to plug our QDS/QKD systems into this at some point in the near future and carry out local tests within the UK instead of having to travel to Japan or to China to do these. And also, it would be a nice idea to commercialise this in some form. So if there's anybody out there with the ability to do this in a commercial approach or in chip-scale technologies, if they could maybe get in touch with me, that would be great. And I'll just wrap up by saying I know most people here are either a PhD or a postdoc, but we have a few positions available in our group. There's experimental QDS, which is working on the experimental side of what I've been talking about. Theoretical QDS, devising new protocols and analysing the results that we generate. And also experimental quantum-enhanced imaging, which is completely different from what I've been talking about, but is still using many of the same technologies. These are available for UK and EU applicants. Unfortunately, only UK applicants can get 3.5 years tuition fee and stipend. EU applicants may only be able to get the tuition fees paid. Thank you very much for your time. I think there's one back down there.
One of my friends in banking once told me they only actually check the signature on checks when it's over £10,000 because of the resources required to check them. Are there any limitations in terms of the resources required to do quantum digital signatures? And what's value would you put on the check?
What value would I put on? Well, let's see. That's a question of scale. Obviously now we're doing this sort of experiments in research laboratories. So you need trained PhD students and postdocs to build the equipment, to build the setups, you need all the expensive equipment to run it. However, it's economics of scale. I think as we go on and we start to develop these technologies and they start to become more widespreadly adopted, I think more people will start to develop technologies for them and the cost will come down. We're at the early days of commercial quantum key distribution hardware now. There's very few companies that will actually sell you them, and the prices are kind of price on asking. They don't really give you a list price for them. But I think as people adopt it more, that'll bring the price down. So you're asking me to put a value on the check to be signed with quantum digital signatures. That would come down to how many checks of that value you would get in a certain time frame, because you wouldn't load the cost entirely onto one check, would you? I think essentially what you do is you take the cost of the hardware divide it by the timescale over which you want to repay it, and divide it by the number of checks that would be written in that time, and that would give you an approximate value. I wouldn't want to hazard a guess at exactly what that would be because I'm not an expert in banking, but there's a calculation you could use to work it out.
Any other questions? I'll ask. So, what are some challenges you see towards commercializing this technology? Like, what are the big things versus say QKD?
Versus QKD.
In terms of integrating.
Well, there's nothing really versus QKD. Once you can do QKD, so long as you build your analysis software correctly, then you essentially now get QGS for free. But you operate at lower bit rates because we're using many pulses to sign bit. So there, I think if you just use base QKD hardware, you would effectively be constricting yourself because, as I said, the number of phases in your alphabet is one of the security parameters in the analysis, and that plays off against the length. If you use QKD hardware that allows you to increase the number of phases in the alphabet, then you can reduce the length, and it means that it starts to become faster and faster in operation. So I think it's a trade-off between what you want to do in terms of bit rate. Some people may be turned off by the fact that it is less efficient in terms of bit rate. But if there was a way to increase the phase alphabet in the QKD systems, then that would be something that would allow you to shorten the length and get to comparable bit rates. I should also say that these protocols are still under revision. And these are what are called direct quantum digital signature protocols. There are newer quantum digital signature protocols that are in work that will be far more efficient than these, but unfortunately they're still at the pre-press stage. So I can't say too much about them, but they should be more efficient than the ones I've presented here.
And you said that you put epsilon parameter on all three components of digital signature, and then you have 1 bit per 40 hours. But if you put just one parameter strict and the other, for example, not so strict, will it be faster and will it be exponentially faster?
Yes to both questions. It will be faster and it will be exponentially faster, yes. It's a trade-off that we chose to make all of the parameters equally important, just because we didn't see any value in weighting it. If your application, you felt you could weight it, then yes, you could speed things up.
Any other questions? If not, let's thank the speakers.